Thank you, Anish. I cannot tell you how wonderful it is to be back in Houston. This is a picture of me and DeBakey at 18 years old. There I am over there, you can see, when I was a member of the Baylor Surgical Laboratory Program over the summer. I came back 3 years later to do an anesthesia preceptorship, and my boss at the time, Dr. Perry Lozon, is in the audience today as well. So this is always coming home for me to come to Houston. So I really thank you for the opportunity and the privilege of coming back. I don't know if showing a picture of DeBakey in this room is allowed, though, but you know, we can talk about that later. My disclosures: I did write these books for the general public. I am the chief medical officer of these 4 companies and a paid advisor to these other 4. I'm not going to be discussing any of these during the course of the talk. All right. My goal today is to try to tie together various aspects of chronic disease in different venues. Now, I take it none of you are dentists here today. There is a dental school at Texas Medical Center, but it's the other side. It's UT Houston, not Baylor. So hopefully this will not be sort of repetitious for you. I always feel funny talking to dentists about cariology. It's like bringing coals to Newcastle, but hopefully this will be relatively new for you. I am not, okay, there we go. So, anybody recognize this? Looking in people's mouths. This is relatively common here in Texas, unfortunately, called Mountain Dew mouth. Well, unfortunately, we have Mountain Dew mouth in 18-month-olds as well. And we have the same diseases in adults as we have in children. And this is a marker for the problem. Now, the thing to know about dental caries is that this is a relatively new phenomenon. If you look at fossils from various times going back, way back into the Paleolithic and Mesozoic eras, dental caries were almost non-existent. And you can see that basically it was a pretty darn low frequency and prevalence. It's only since the Industrial Revolution that things really took off. And there we go. In 1934, perhaps the most seminal, to this day, symposium on dental caries occurred in New York City. And there were 2 camps. There was the camp of hygiene, that is, clean teeth do not decay, and they had some heavy hitters at the time, including Thaddeus Hyatt and Maurice William. These were big names in the field in those days. And then there was the people who thought nutrition mattered. Okay, so if you will, team nutrition. And we had some big names there as well, including the ever-present Weston Price. And to this day, there's a Weston Price Foundation that is pushing the concept of diet and chronic disease. So we had these 2 groups duking it out. What causes dental caries? So there were the people who said that clean teeth do not decay. Well, let's look at what was in our mouths. And you can actually look at the DNA footprinting of the various organisms that have been found on fossils. And what you can see is that the phyla in the mouth have changed over the course of time. And in particular, I want you to alert you to this blue one. You'll notice that way back in our hunter-gatherer days, this blue one, Firmicutes, was actually relatively common in the mouth. Now it's pretty much gone. Well, where is Firmicutes today? It's in our intestine, and it's actually one of the bad guys in terms of making cytokines that drive chronic metabolic disease. When we talk about the microbiome, when we talk about the bad bacteria, we're mostly talking about Firmicutes. Well, it used to be a denizen of our mouths, and now it's a denizen of our intestines. It got chased down there. And if you notice, also proteobacteria didn't even exist back then, and now it's taking up most of our mouths. So our flora have changed as we've evolved, and the question is why? In particular, this guy over here in purple has been a major thorn in dentists' side. He is known as strep mutans, and this is the primary driver of dental caries. But it wasn't even part of our mouths. So if you look at bacterial diversity in the mouth, you'll notice that it was relatively constant all the way through, and it's only from medieval to modern times that bacterial diversity has actually gone down as strep mutans over here has made its ugly presence felt. So clearly it's being responsive to some aspect of changes in our environment that have gone on. All right. Now, what about the hygiene the diet hypothesis, the nutritional hypothesis? Well, we know from numerous studies now going back at least 70 years that sugar, that is dietary sugar, sucrose, the stuff in your tea, your coffee, the crystals, etc., are a primary driver of tooth decay. And it is both a dose and a chronicity phenomenon, as you can see here. Here's dose and here's chronicity in terms of post-eruptive tooth age. And you can see here that there is a log linear relationship between sugar consumption and caries incidence. Different carbohydrates are fermented at different rates and lead to different changes in pH. And the ones that you'll notice are the most cariogenic, that is fructose, glucose, sucrose, are the ones that drive the pH lowest. This thing called the Stefan curve. This is old news to the dentist. They know this stuff very well. Now, when you actually look at the data, it turns out those people eating starch but a low sugar diet, which is a lot of people in the gatherer countries, have a very low incidence of caries. It does not appear to be relative to starch. But as soon as the sugar goes up, that's when you get the high incidence of caries. And when you actually look at the changes in the tooth, you can see that starch plus sucrose is what changes the amount of protein, the amount of external polysaccharide, okay, the cytokines in the mouth, if you will. And when you actually look here, sucrose and starch and sucrose are the things that cause the change in the baseline pH, not starch alone. You'll notice that the pH only goes down when sucrose is added. It's not the starch. So it is not the carbohydrate, it's the sugar. Now, in 1939, one of those nutritional dentists, McCullum, famously said this: it seems that were we to turn to a low-sugar, high-fat type of diet, such as is prescribed for diabetic patients, and I want you to read that again. This is 1939. Low-sugar, high-fiber type of diet prescribed to diabetic patients. Do you prescribe that to your diabetic patients today? Okay, we knew this a long time ago, and we're only now rediscovering it. This is old news. We might expect a prompt and marked reduction in caries susceptibility. This type of diet is practical in many countries, but fats are in many regions considerably more expensive to produce than are starches and sugars, i.e. pasta. At any rate, we now know how to produce good teeth as respects structure and how to preserve them in considerable measure from decay. 1939. This is old news. However, this is what happened in the meantime. Okay? And the reason it's happened is because of changes in price. And you can see that here's the consumer price index for food in general in yellow. But this is the consumer price index for fruits and vegetables, having basically doubled over that time. And here, down here, is the consumer price index for ultra-processed foods, being 1/4 that of the healthy food. So we have basically driven this through changes in food subsidies that allow for ultra-processed food to be much cheaper than real food. William Davis, another one of these nutritional dentists, in 1941 said this: "We realize very well, however, that if sugar is the great offender in the cause of dental caries, as seems to be the case, we have a very difficult task ahead in making such progress in its control by the reduction of sugar intake so far as the mass of people is concerned." And here's the key sentence: Most people would prefer some decay rather than to eliminate the sweets. Duh. Truer words were never spoken. We should keep up the admonition and give the evidence as to its harmful effect on teeth. At the same time, let us hope our research workers discover a more practical means of controlling or preventing tooth decay. Well, they didn't have long to wait, because by 1947, something else had appeared on the scene. We had Team Hygiene, we had Team Nutrition, well, now we had Team Tooth, who were advocating the use of fluoride. Now, fluoride has benefits in terms of the mouth, because what it does is it reduces the amount of time spent at low pH, as you can see here. This is with fluoride, okay? And it also fluoridates the calcium hydroxyapatite of the tooth, making it harder for those bacteria to burn a hole in the teeth with lactic acid. So there is no question that fluoride has beneficial effects in terms of tooth decay. The question is, was it enough? Well, in 1945, Grand Rapids became the first city in the world to fluoridate its drinking water. During the 15-year project, researchers monitored the rate of tooth decay amongst 30,000 school children. After just 11 years, Dr. Trendley Dean, who is now director of the NIDR, National Institute of Dental Research, announced an amazing finding. The caries rate amongst Grand Rapids children born after fluoride was added to the water supply dropped by more than 60%. This finding, considering the thousands of participants in the study, amounted to a giant scientific breakthrough that promised to revolutionize dental care, making tooth decay for the first time in history a preventable disease for most people. Now, we take this for granted. This was a big deal. This was a BFD back then, because this was a huge issue that was actually the primary driver of outpatient anesthesia and dental visits. And so they started fluoridating the drinking water around the world, and what you can see is that as they did it, dental caries prevalence went down. Indeed it did. And so they then started putting it in the toothpaste. And you can see that when they added it, dental caries were lower. No argument. Fluoride improves the prevalence rate of dental caries. However, at our best, we only showed a 30% reduction. Now the question is that good enough? Well, so they went up on the fluoride dose to 5,000. And guess what? It only showed a 40% reduction. In other words, we never even broke 50%. And we've reached an equilibrium. So if you take a look here in terms of dental caries in prevalence in toddlers and in teenagers, okay, basically we can get rid of about half the dental caries with fluoride. The question is that good enough? Well, dentists seem to think it is good enough. Why is it that dentists are happy with a 40 to 50% reduction in dental caries? Well, I'll tell you who's not happy about it. The Department of Defense. And here's why. Because 42% of recruits to the armed forces can't be deployed into the field because of class 3 dental caries, because the risk for dental abscess in the field is too great. This is actually a national security issue, type 3 dental caries. And it's easy to fix. This was done by a colleague of mine, Simon Thornley, in New Zealand, where they basically took 2 school districts and they took the sugar out of kids' diets at school and showed that at any given age, 8, 9, or 10, the Yandara school district had a lower prevalence of caries than the control school district. And when they did the multivariate analysis, the thing that made the most difference was which school they were at. The one with the sugar in the diet or the one without the sugar in the diet. So we know what to do to fix this problem. And now there's even concern that fluoride might be toxic. In fact, we've always known fluoride is toxic. We knew that back in 1909. Fluoride is actually the manifestation, the toxic byproduct of aluminum mining. Okay? We've known that fluoride is toxic for years. And it now looks like increased fluoride concentrations in the urine of pregnant women predict reductions in IQ in their offspring. So we may have been poisoning the entire population. Anybody ever see Dr. Strangelove? Okay. One of the generals actually says that, fluoride is a communist plot. There may have been some truth to it. Not totally. But in fact, it's not necessarily all that it's been cracked up to be. And so the question is, we put a lot of stake, a lot of money into this fluoride business. And the question is, why? Well, yeah, because it works, but there's another reason, a more, shall we say, sinister and pernicious reason. And the reason is because the National Institute of Dental Research was basically influenced from outside by the sugar industry. And my colleagues at UCSF, Kristen Carnes, Laura Schmidt, and Stan Glantz, actually found the papers, found the track record, the paper documentation that showed that the scientific agenda on the National Institute of Dental Research's research program was actually being modified back in 1971 by the sugar industry. Anybody ever hear of a caries vaccine? In 1971, the NIDR put 75% of its research budget toward a caries vaccine. Well, how's that caries vaccine working for you? Okay? This is what happened. Now, the reason I present all of this stuff about cariology to you is because the same thing has happened to you. And you're going to see how this plays out over the course of the next half hour. So now let's talk about something a little closer to home for you, cardiology. So, one of the primary drivers of cardiac disease is type 2 diabetes. So this is a paper that was released in 2001 in Nature, looking at 2,000 data, looking at how many diabetics were walking the earth back in the year 2000. 151 million diabetics walking the earth. And it was projected that that prevalence would go up to 221 million 1 decade later, 2010. That would be a 46% increase, or an annualized inflation rate of 3.88%. This is not what we saw. What we actually saw was 285 million for an annualized inflation rate of 6.55%. By 2014, with all of the media attention, and with all the gym memberships, and with all the changes in schools and what have you, we were up to 422 million. By 2019, we were up to 469 million. Last year, 537 million, and now what is projected for 2030 is 568 million people with diabetes. And they are chewing through all of the healthcare resources and all of our dollars, to the point where now healthcare will be 20% of the entire US budget. And we can't afford that. WTF. How can this be happening on our watch as we are trying to do something about it? And the reason is because we haven't done anything about it, because we haven't addressed the problem. Now, you could say, well, we have done something, because in fact, heart disease has gone down. And that is true. And you could say, well, statins are the cause of that. Maybe that's true, maybe not. Okay? What's taken its place instead is diabetes, as you can see on the right. So we've traded in one disease for another. And heart disease, and you can say what you like, because this is Texas Heart Institute, and your goal is to save people. But you know what? People with heart disease die fast, as opposed to people with diabetes, who die way slower and cost way more. Now, if you look at where the money goes, so here's hospital costs in red, here's physician costs in green, and here's pharma costs in purple. They do not add up to the total cost, because the rest of it is going to the care and treatment of chronic disease, like type 2 diabetes. So these are the two inconvenient truths that we as a medical profession and we as a society have basically thrown in the garbage can. There is no medicalized prevention for chronic metabolic disease. None. Think about it. You got a cure for type 2 diabetes, do you? You got a cure for hypertension. You got a cure for cardiovascular disease. You got a cure for cancer. You got a cure for dementia. You got a cure for fatty liver disease. You got a cure for polycystic ovarian disease. Is that right? What we are doing is we are papering over the symptoms of each of those. We have drugs that treat the symptoms. We have no drugs that treat the cause. It's like giving an aspirin to a patient with a brain tumor because they have a headache. Might help the headache, ain't going to do a damn thing for the brain tumor. And that's what we have been doing for the last 50 years. The second inconvenient truth is you can't fix health care until you fix health. You can't fix health until you fix diet. And you can't fix diet until you know what the hell is wrong. And we have been barking up the wrong tree for the last 50 years. And the question is, why? Why have we been barking up that wrong tree? And that will be the second to last slide. So let's look at the data. How do we know we're barking up the wrong tree? Well, here's a study that came out in 2017 that probably a lot of you are familiar with, called the PURE study, the Prospective and Urban and Rural Epidemiology Study. Salim Yusuf is the primary, PI on all this. And you can look. Okay, here's cardiovascular disease, total mortality and morbidity from total fat, saturated fatty acids, monounsaturated fatty acids, polyunsaturated fatty acids, and finally from carbohydrate. So if the curve goes below the horizontal line, it's protective. If the curve is above the horizontal line, it is causative. Notice, pick your fat. All protective, each one. The only one that's above the line is carbohydrate. Now I want you to take a close look at this. This is a picture I took in a Rome restaurant window of Italian beef, Argentinian beef, and US grade A prime choice Texas beef, right there, corn-fed beef. So what do you see? Homogeneous marbling. Now we love that marbling because that's where the fat is, that's where the flavor is. And you can cut that Texas beef with a butter knife. And we sell it around the world. What is that? That is intramyocellular lipid. That is fat inside the muscle. This animal has metabolic syndrome. That's why it can go from birth to slaughter in 6 months, whereas the Italian and Argentinian cows take 18 months to go from birth to slaughter because they're feeding on grass in the Mendoza Valley instead of on corn in a CAFO. Okay? Well, that's what's happening to us. This animal has metabolic syndrome. We just kill it before it gets sick. Now, people say, well, you know, it's the saturated fat or but actually, it's not the saturated fat, because if you actually look at the hazard risk ratio for type 2 diabetes, once you factor out the heme and once you factor out the antibiotics, in fact, the hazard risk ratio goes down to 1.13. Same true for chicken, same true for fish. Once you factor out what we fed the animal, it actually disappears, that effect. One of the reasons is because of these branched chain amino acids. Now, branched chain amino acids are essential amino acids, leucine, isoleucine, valine. You need them to grow muscle. 20% of your muscle is branched chain amino acids. So if you're a bodybuilder, you know, you put your scoop of protein powder in your smoothie and mix it up, and you need those branched chain amino acids in order to be able to make muscle because they're essential. You have to eat them. You can't make them. And that's true. However, what if you're a mere mortal like me and you eat excess branched chain amino acids because you have a Texas-sized corn-fed steak? Where do the excess branched chain amino acids go? They go to the liver deamidates it, okay, and turns that branched chain amino acid into a branched chain organic acid, which then ends up in the TCA cycle, gets thrown off as citrate, and you turn that into liver fat, driving insulin resistance. So all those branched chain amino acids that we are consuming because we consume corn-fed beef, chicken, and fish are actually contributing to the problem. So it's not the meat, it's what we did to the meat that matters. Another problem, which you're probably familiar with, so work that's been done by Stanley Hazen at Cleveland Clinic, is that meat, muscle, is very high in choline. Now we need choline, it's vitamin B4, okay? We don't call it that, we call it choline now, but it was vitamin B4. And the choline is necessary because you need to make phosphatidylcholine in order to make ApoB100, in order to export and transport fats around the body, and you also need it for acetylcholine, for neurotransmission. So you need choline, but what happens to excess choline? It gets metabolized in the intestine by microbiome to trimethylamine, TMA, which then goes to the liver and gets oxidized to TMAO, trimethylamine oxide, which is the stickiest substance in our bodies and lines our arteries and has been shown to be, at least in animal models, the primary determinant of cardiovascular plaque. Now, we say that saturated fat is bad, but you know what? There are two saturated fats. There's red meat saturated fat, palmitate and stearate, even chain fatty acids, and then there are odd chain fatty acids, pentadecaenoic acid and septaenoic acid, which turns out, remember the curve going down below the horizontal line? Turns out those are actually protective, and those are in dairy. But we threw the dairy fat out with the red meat fat when we went low fat, right? We took the fat out of the milk that we gave the kids, right? Now they've got skim milk, and skim milk tastes like dishwater. The kids wouldn't drink it. So what did the dietitians at the schools say? Well, they got to drink their milk because they need their vitamin D and calcium. So what they put in? The chocolate and the strawberry. So we took something that was protective out and put something that was harmful in. Now let's look at surrogate markers. So everybody is worried about LDL. You guys are worried about LDL. This is Texas Heart Institute. LDL is a problem. Yeah, it's a problem. I'm not saying it's not. Okay, but if you take a look at the meta-analyses, high LDL correlates with cardiovascular disease with a hazard risk ratio of only 1.3. 30% increase in cardiovascular disease based on a high LDL. Now, the public health experts say 30% increase, that's a public health problem. Okay, and I'm not dismissing LDL as a problem, but 1.3. When you look at LDL cholesterol, turns out it's not the LDL cholesterol that matters. It's the LDL particle number that matters. Because here you see high LDL cholesterol, high particle number, Kaplan-Meier curve shows increased mortality. But here's a high LDL particle number, low LDL cholesterol, same mortality. Whereas those with low LDL particle numbers, in other words, less LDL in each particle, ends up being much safer and with a much better longevity. And the reason for this is because there's another particle which is way more important than LDL, and it's triglyceride. So the hazard risk ratio for triglyceride in heart disease is 1.8, as you can see here. Now, what is triglyceride? Well, it's two things. It's either VLDL or it's chylomicrons. Now, if you're fasting, the assumption is your chylomicrons have cleared, in which case then your triglyceride, your fasting triglyceride, is your VLDL. Now, where did your VLDL get made? Did you eat it? Or did it get made somewhere? Turns out it's all from the liver. VLDL is your liver output of fat. Now, we also have these other species, and we're going to talk about IDL in just a moment. LDL, and it turns out there are two LDLs, and we're going to talk about that in a moment. And then finally, HDL, which for the most part is, shall we say, good. So, turns out that IDL, remnant cholesterol, after the triglyceride has been offloaded into adipose tissue, we call that remnant cholesterol. Turns out remnant cholesterol is way more important than LDL ever was. So if you look at these curves in terms of cumulative incidence of heart disease, it's the remnant cholesterol that makes the difference in terms of who gets heart disease and who doesn't. So these are the remnants. And you'll notice the remnants can be chylomicrons because of ApoB48, or they can be the remnants of VLDL, B100, or IDL, after triglycerides have been offloaded. And if you look at the source of cholesterol remnants, take a look. So here's cholesterol remnants, IDL, VLDL, chylomicrons. It's almost all triglyceride. The LDLs are mostly cholesterol. So actually the triglyceride, the fatty acids, are more important for atherogenesis than the cholesterol is. And that makes sense in terms of this LDL particle number versus LDL cholesterol. Now, why is this? And why do we have this conundrum? Why are all the lipidologists going, berserk over this? And the reason is because LDL is not one thing. It's two. So here's an electrophoresis, and here's what we would call pattern A, or large buoyant LDL. And over here, down here, we have pattern B, or small dense LDL. Now, if you talk to the people at Harvard School of Public Health, they will tell you they do not believe in small dense LDL. They say small dense LDL is not the atherogenic particle. They say it is associated with the atherogenic profile, but it is not the atherogenic particle. I don't even want to get into that. Okay? I don't know if it's the atherogenic particle or not. I do know that it is associated with those remnant cholesterols. So if it's the remnant cholesterol, if it's the small dense LDL, you guys figure that out. You tell me when you're done. Okay? But in the meantime, it turns out that there are two profiles. There's this profile of pattern A LDL, and the way you figure that out is by looking at the triglyceride. So low triglyceride, high HDL, you've got pattern A. This is large buoyant LDL over here on the left. Conversely, here's the atherogenic phenotype, and here's pattern B, and you can see that's high triglyceride, low HDL. So it's that HDL, it's that triglyceride to HDL ratio that seems to matter, and that's actually a surrogate measure for a metabolic phenomenon, insulin resistance. Your TG to HDL ratio and your fasting insulin correlate with an R value of 0.76. So what you were looking at when you were looking at the lipids is not the lipids. What you were looking at is the metabolic status of that patient. And you need to interpret it in that light, as opposed to just looking at a value. And that's where we get into trouble. Now, if you look here, you'll notice that HDL goes down with added sugar, and triglyceride goes up with added sugar. So that TG to HDL ratio is very responsive to sugar consumption. And you can see here in a meta-analysis on sugar and triglycerides, there's your diamond not crossing the identity line. Sugar is a driver of those triglycerides, and those triglycerides are a primary driver of cardiovascular disease. I think we've now established that. Okay, now those are all the surrogate markers. Now let's look at the randomized clinical trials. Here's the Women's Health Initiative. It was stopped because not only did it not work, but it actually made people worse. And you can take a look here. We're looking at LDL, and we're looking at whether or not it actually helped, and it didn't help at all. Okay? Going low fat did not help anybody. And I think you all know that. What about drug trials? So this is a meta-analysis of 41 drug trials, randomized control trials, or dietary interventions, 41 and 3, for primary prevention of heart disease, not secondary. That's different. Primary prevention, just taking the large population, no overall benefit of mortality. In fact, those who received a statin for primary prevention, do you know what their increase in lifespan was over those who didn't? 4 days. 4 days increased lifespan for taking a statin. Is that worth it? And these trials did not reduce CVD events in the primary prevention population. And some of the studies reported harm. In fact, here's mortality, here's myocardial infarction, here's stroke because of the statins, not because of the heart disease. And if you look here at the meta-analysis of statins and risk reduction, here's all death. Okay? For primary prevention, no difference. For secondary prevention, so if you've already had a heart attack, big difference. So, if you've had a heart attack and your LDL's high, by all means go on a statin. But if it's primary prevention, oh, your LDL's of 150, you need a statin. Well, that's what the American Heart Association today says. And they say it for 8-year-olds. I got a problem with that, because there's no data that supports that. And the incident diabetes rate, as you can see here, is 20%. So you're making things worse because, after all, what is a statin? It's a 3-HMG-CoA reductase inhibitor. It's a mitochondrial enzyme. You're poisoning your mitochondria. No wonder you've got hyperglycemia. You can't even metabolize the glucose. So giving a statin just because your LDL is high, to me, makes no sense. I think we're actually doing harm rather than good, because you can do much better for people's reduction of heart disease by getting rid of the triglyceride than by getting rid of the LDL. So the question is, how do you get rid of the triglyceride? Well, here's an article that was an editorial, and these are not exactly, shall we say, fly-by-nights. This was written by my colleague Asim Malhotra, who's a member of the National Health Trust in the UK, Rita Redberg, who is currently editor-in-chief of JAMA Internal Medicine, and Pascal Meyer, who's currently editor-in-chief of BMJ Open Heart. And this is what they said. Saturated fat does not clog the arteries. Coronary heart disease is a chronic inflammatory condition, the risk of which can be effectively reduced from healthy lifestyle interventions. And what they say is that primary pathology is insulin resistance. Insulin resistance is a metabolic problem that leads to a cardiac outcome, a cardiometabolic disease. Emphasis on the word metabolic. Fix the metabolism, you'll fix the heart. So the question is, what's the reason? What's the cause? That's where I come in. So this is an article that was written in the New York Times Magazine, cover article, in 2011 about our research at UCSF, written by Gary Taubes. Is sugar toxic? And this is our article that we published in Nature shortly thereafter, called The Toxic Truth About Sugar, that I wrote with my colleagues from the Institute for Health Policy Studies at UCSF, Laura Schmidt and Claire Brindis. So, do we mean toxic? People say to me all the time, oh, come on, sugar, toxic, how is that possible? It's calories, it's energy, it's 4th of July and apple pie and Valentine's Day. How can it be toxic? Well, let's look at the word toxicity. This is the definition right out of the dictionary. The degree to which a substance can damage an organism. Notice it does not distinguish acute from chronic toxicity. So we have acute toxins like sarin and ricin and VX gas, okay? Parts per billion, keel over and die in a nanosecond, okay. We also have chronic toxins like carbon tetrachloride or benzene or cigarette smoke, okay? Where arsenic, where one exposure won't kill you, but 10,000 exposures might. Well, that's basically what we're talking about with sugar, okay? It's not one exposure. It's not one sugar meal that's going to kill you, but 10,000 just might. Now, in order for me to establish this, I have to show that sugar is an independent risk factor, that it's independent of its calories, otherwise calories are toxic, and we know that's not true. That it has to be independent of obesity, because therefore then obesity would be toxic, and we have metabolically healthy obese people. So that's not true. And I must establish causation. Correlation is not enough. Correlation will not do. Okay, now there are a lot of critics. They say, well, it's animal models, not human studies, and you have to give enormous amounts of fructose, the sweet molecule in sugar. So I'm going to limit my discussion now to human data only, human consumption only, in doses routinely ingested by humans and controlled for calories and obesity. Okay? So here's the mortality risk based on NHS data and pooled data, and you'll notice for sugared sweetened beverages, not crossing the identity line, so that's correlation. I need to show you plausibility, I need to show you mechanisms, I need to show you correlation, and finally I need to show you causation. And I got to go fast because I'm looking at the clock. So the reason, why does this happen? It's not in the heart, it's in the liver. So here we have normal liver, okay, sinusoids, bile canaliculi, Kupffer cells, and here we have fatty liver disease. Fat vacuoles, macrophages, the beginning of scarring. Okay, the problem is if you look at this histologically under the microscope, you can't tell what did this. Was it alcohol? Prior to 1980, it was alcohol. But now, today, 45% of all adults and 25% of all children, not obese adults, not obese children, all adults, all children have fatty liver disease. This was a disease we'd never even seen before 1980. So this is probably the visual I want you to take away from today's talk. Okay? Here we have an MRI fat fraction map. So you can see the fat really easy. So here's an obese person, but I want you to take a look at this guy's liver, nice and dark. 2.6% liver fat. This is fine. This is a metabolically healthy obese, MHO. This guy might outlive you. Now here's what you would more likely expect to find. Obesity, but take a look at this guy's liver. 24% liver fat. This is fatty liver disease. This is metabolic syndrome. No argument. This guy's got a problem. Now take a look at this guy. Notice normal levels of sub-Q fat, but take a look at his liver. 23% liver fat. Thin sick, fat healthy. So it's not the fat you can see, it's the fat you can't that matters, and in particular the fat in the liver. Turns out that fatty liver is the liver expression of metabolic syndrome, because NAFLD and metabolic syndrome are congruent. It goes along with large waist, high glucose, low HDL, high triglycerides, high blood pressure, and the more obese you are, the worse it is. No argument there. And it's true for adults here, and it's true for children down here. All true. Well, here's a good tie-in with how the talk started. Turns out, tooth disease correlates with NAFLD, because ultimately they have the same cause. So it shouldn't be surprised that, in fact, periodontitis and dental caries are predictive of NAFLD. Okay? NAFLD is a primary predictor of type 2 diabetes. If you have fatty liver disease, you are 3.5 times more likely to develop diabetes in your lifetime. Now, the question is, where'd that fat come from? Prior to 1980, if you had fat in your liver, it was alcohol. But it ain't alcohol now because kids get it. And kids don't drink alcohol, mostly. So, where did it come from? So, this was a study done by at WashU, Sam Klein's group. And what they did was they measured visceral fat and liver fat on MRI. And when they held the liver fat constant, the visceral fat did not explain the insulin kinetics. Whereas when they held the visceral fat constant, the liver fat explained all the kinetics. It's the liver fat that's driving the insulin resistance. And it makes sense that that would be the case, because after all, where does the pancreas drain into? Does it drain into the inferior vena cava? No, it drains into the liver, because the liver is the primary target of insulin action. And when your liver doesn't work right, your pancreas has to work harder. Okay? It's a reflex that's set up. So the question is, okay, where did that fat in the liver come from? And the answer is here. Notice in gray, non-systemic fatty acids. Now, we know where systemic fatty acids come from. They come from diet, or they come from lipolysis of peripheral adipose tissue. But non-systemic, where does that come from? Well, that comes from right in the liver. You're making it right there. And how does that happen? Well, Here's what happens in the liver to glucose. It goes to glycogen. And glycogen is, for lack of a better word, safe. Here's what happens to alcohol. Alcohol does not go to glycogen. Alcohol comes down to the mitochondria as acetate, overwhelms the mitochondria's ability to be able to metabolize it via the TCA cycle, throws off the excess as citrate, exits the mitochondria through a process known as the citrate shuttle, and then that citrate will act as the substrate for these three enzymes: ATP citrate lyase, acetyl-CoA carboxylase 1, fatty acid synthase. These three enzymes together form what we call DNL, de novo lipogenesis, new fat making. This is how alcohol gets turned into fat in your liver. Now, some of the fat will come out as VLDL, and so that's the hypertriglyceridemia of alcoholism, and some of it won't. Some of it will get stuck. Some of it won't bind to ApoB100, and it will precipitate as a lipid droplet, and now you have alcoholic fatty liver disease. Everybody with me so far? Well, now let's look at fructose. So fructose enters the liver. You see glycogen anywhere? No glycogen. Comes straight down to pyruvate, enters the TCA cycle, and the same thing happens that happened with alcohol. You end up with de novo lipogenesis. You end up with VLDL. This is the hypertriglyceridemia of sugar consumption. Some of it won't make it out, precipitate as the lipid droplet, and now you have non-alcoholic fatty liver disease, and we have that in children. Okay, so can we prove that sugar is the cause of diabetes? Working up to it. So we're going to start with correlation. Well, here's juice. Juice increases hazard risk ratio for type 2 diabetes in the nurses study. Here's the EPIC Interact study out of Europe. Sugar sweetened beverages increase risk for diabetes by 29%. Every sugar beverage consumed per day increases diabetes risk by 29%. And we don't drink one sugar beverage a day, we drink 2.5. So take that up to 68%. Now remember, these are all correlation, and I'm aware. Sugar beverages, fruit juice, doesn't matter. 95th percentile confidence interval does not cross 1. This is in adolescents out of the NHANES data that we did, showing that as the sugar quintiles went up, so did our risk for metabolic syndrome in teenagers. Okay, can we prove causation? Now there are two ways to prove causation. There's randomized controlled trials, good luck with that in terms of sugar. And there's another way called econometric analysis, where you do a natural history study and you look at the change in prevalence over time and account for all of the confounders, which is what we did by looking at the changes in the FAO, Food and Agriculture Organization statistics database for type 2 diabetes worldwide over a decade. And what we showed was that only changes in sugar availability predicted changes in diabetes prevalence. If you consumed an extra 150 calories in food, your diabetes prevalence went up a total of 0.1%. But if those 150 calories happened to be a can of soda instead, diabetes prevalence went up 11-fold, 1.1%. And again, we're drinking 2.5 of those. This study actually meets the Bradford Hill criteria, which should all be well known to you, because that's the level of criteria we have for tobacco and lung cancer, and for tobacco and heart disease, is the Bradford Hill criteria. Because we showed dose, more sugar, more diabetes. We showed duration, longer sugar exposure, more diabetes. We showed directionality. Those countries where sugar went up, more diabetes. Those countries where sugar went down, and there were 10 of them, less diabetes. And most important, you have to show precedence. If something follows something, it can't be a cause. It has to precede. Okay, that's why you need the time component. That's why it's an econometric analysis. And we had it because we had 10 years of data. 3 years. Whenever sugar changed, diabetes changed in the same direction 3 years later. And finally, causation. So this is work done at Harvard, at Joslin, where they showed that glucose actually increases mitochondrial beta oxidation. And it does so by activating two enzymes, AMP kinase, the fuel gauge on the liver cell, and HADH, hydroxyacyl-CoA dehydrogenase, the sum total of which increases beta oxidation. So glucose, for lack of a better word, is good. Fructose, on the other hand, that sweet molecule in sugar, suppresses 3 enzymes involved in fatty acid beta oxidation. It suppresses AMP kinase, it suppresses acyl-CoA dehydrogenase long chain, which is necessary to start the chopping up of fatty acids into their 2 carbon fragments, and also, through uric acid, it inhibits carnitine palmitoyl transferase 1A, the shuttle mechanism for fatty acid import into the mitochondria for beta oxidation. Ron Kahn himself said the most important takeaway of the study is that high fructose in the diet is bad. It's not bad because it's more calories, but because it has effects on liver metabolism to make it worse at burning fat. As a result, adding fructose to the diet makes the liver store more fat, and this is bad for the liver and bad for whole body metabolism. We did a controlled trial of fructose restriction. These are 3 of our 5 papers. And what we did was we took the sugar out of kids' diets for 10 days. We took their percent calories as added sugar from 28% down to 10%. We gave them fruit. Now, if you do this, you're going to lose 400 calories a day out of the diet, in which case, after 10 days, patient might lose weight. We didn't want them to lose weight. We wanted them to stay the same weight or gain weight. Because if they got better and they lost weight, the critics would say, well, of course they got better, they lost weight. We wanted them to stay the same weight. So we had to give them back the 400 calories equicalorically. We gave them extra starch. We did a starch for sugar exchange. We did a glucose for fructose exchange with no change in calories, no change in weight. We studied them baseline, we studied them 10 days later. Every aspect of their metabolic health improved at baseline. Here's their oral glucose tolerance test. Glucose area under the curve down 8%. And here's their insulin response. Notice insulin resistance at baseline. And now they actually have a lower insulin response, even though they're consuming more glucose. And they now have better clearance, too. In other words, they're more insulin sensitive. We wanted to see what the liver was doing, so we gave them C13 labeled acetate, which would then get incorporated into palmitate, so we could measure de novo lipogenesis. And sure enough, de novo lipogenesis got cut in half. And finally, fat depots. So notice, no change in subcutaneous fat, because we didn't let them lose weight. 7% reduction in visceral fat. 22% reduction in liver fat, with no change in calories, no change in weight. And as the calories, as the fat in the liver went down, as you can see here, 22% in liver fat, their pancreas started making insulin properly. In other words, we reversed their metabolic syndrome, not by making them lose weight, not by changing their calories, but by changing the carbohydrate concentration, by changing the carbohydrate partitioning. This has now been corroborated by another group at UC San Diego and Emory. And finally now, sugar and heart disease. So, everybody remember those small dense LDL? Here they are in red. See them? This is day 0. Here's day 10. Gone. Here's another patient. Here they are at day 0. Here they are at day 10. Gone. By the way, HDL went way up, as you can see here in green. So when we actually looked at it, so here's their LDL size getting bigger, remember, large buoyant, okay? Here's their small dense LDL going down, okay? Their ApoC3 went down 49%, their ApoB went down 32%, their TG to HDL ratio went down 38%. These patients are more metabolically healthy. And the change in triglyceride and VLDL correlated with the change in insulin sensitivity. So as their liver fat went down, their lipids got better and their pancreas got better. So this is what the data say. Epidemiologic and randomized control trials do not support a positive association between animal-based fat, LDL, and diabetes. Red meat may be promotive of diabetes, but not because of the saturated fat. Might be the heme, might be the oxidative stress, might be the branched chain amino acids, might be the TMAO. So I'm not telling you meat is a walk in the park, but it's not because of the saturated fat. Dairy is protective, and it's got plenty of saturated fat. Prospective correlational data demonstrate associations between added sugar and diabetes exclusive of calories or obesity. Econometric data show causal medical inference for sugar and diabetes exclusive of calories and obesity, and our interventional isocaloric glucose for fructose exchange showed improvement in all aspects of metabolic health with no change in calories, no change in weight. Now, just so you don't think I'm fructose-centric, there are 4 things in our diet that can do the same thing, that are handled by the liver only, that are not insulin regulated, and no glycogen pop-off, so the mitochondria are overwhelmed. They are trans fats, but we know that and they're coming out of our diet. Branched chain amino acids, leucine, isoleucine, valine, corn-fed beef, chicken, and fish, alcohol, and fructose. So we have causation for sugar and 4 diseases: diabetes, heart disease, fatty liver disease, and tooth decay. We have correlation for cancer and dementia. We're working on those. And here's the denouement. Remember, the dentists were led astray by the food industry when the food industry basically interfered in 1971. Well, guess what? They did it to us too. This is from my colleagues, Kristen Carnes, Laura Schmidt, Stan Glantz at UCSF. They analyzed these these food industry documents, and they were able to show that the Sugar Research Foundation in 1965 paid off 3 professors at the Harvard School of Public Health: Fred Stair, the head of the Department of Nutrition; Mark Hegsted, his assistant, who became the head of the USDA; and a guy named McGandy, to single out fat and cholesterol as a dietary cause of heart disease and downplay the evidence that sucrose consumption was also a risk factor. The Sugar Research Foundation set the review's objective, contributed articles for inclusion, and received drafts, and their funding and role was not disclosed. They did it to us too. And we have been on a wild goose chase for the last 50 years, while our patients have gotten sicker and sicker and sicker. And there's no medicine for this. And it's everywhere. We are awash. We are contaminated. Our entire food system is poisoned by sugar because it is a mitochondrial toxin, and it's also addictive. Processed food, sugar's the payload, ultra-processed food is the vehicle, is an experiment that failed. But that's what your patients are eating because it's cheaper. Processed food is high sugar, low fiber. Real food is low sugar, high fiber. Any diet that works is because it's real food. And I don't care if it's vegan or keto or Mediterranean or paleo or anything in between. Okay? They're all low sugar, high fiber. So is sugar public enemy number 1? Well, trans fats used to be, but we now know that, so now sugar is. So in conclusion, this is a public health crisis because it's an exposure even in normal weight people. Processed food is the exposure. The food industry has adulterated our food supply for profit. The industry has bought off scientists and co-opted critics. Most of the checks and balances have been eroded, and government's been complacent and in some cases complicit. Our best chances are public education and physician education, which we're doing right now, business, okay, because insurance companies are taking the brunt of this, and legal action, which we're working on. So with that, I want to thank my collaborators at UCSF, at Touro, at San Francisco General, at Stanford, and at UC Hastings College of the Law, at Berkeley, and many dentists who've helped contribute to this. And with that, I thank you for your attention. Appreciate it.